Never mind, I just checked with that. Okay. Forget it.
Test. Is it working? Okay, so hello everyone. I'm very happy to introduce Soufiane Hayou. He obtained his PhD at the University of Oxford and is now a postdoc at Simmons. And today he will talk about a theory of scaling. Let's welcome Soufiane.
Thank you. Yeah, so as Kei-Feng mentioned, so today I'm going to talk about an attempt to have like a general framework for scale-aware training, or what I call theory of scaling. So if we look at the state-of-the-art models, language or vision models like GPT, Claude, Gemini, more recently DeepSeek, they all share this common characteristic, which is they're large scale. And by large scale, I mean there is a large neural network behind these models, where like hundreds of billions of parameters. And this neural network was trained on a large training corpus, a large training data set. That could be trillions of tokens, right? This is a figure here of this plot from the Llama 2 paper, which shows the effect of scale, both in the size of neural network, but also the size of the training data set. So the x-axis is the size of the training data set. And the maximum is like 2 trillions. And the color code is the size of the model. So from 7 billion parameters to 70 billion parameters. So you can see that with scale, this is what we call like a train perplexity, which is a measure of how good the model is. The smaller, the better. You can see that with scale, both in data and parameter size, the model seems to improve. So scale is really important. It's probably the most important components in state-of-the-art models. So with this reality, every practitioner who is working on these models, either to train them or fine-tune them, they ask the same question. How can we efficiently train and fine-tune these models? And by efficiency here has a very precise meaning, and it's related to maximizing performance per compute. So given some compute budget, how can we maximize the performance of the model when we use that compute budget? So I'm going to ask you a question. Do you think that theory, and by theory I mean math, do you think it can help solve this efficiency problem, at least improve efficiency? Raise your hand if you think that's. All right, so I'm talking to theorists, that makes sense. Usually I get like less than 30% of people. But so yeah, hopefully by the end of this talk, I will show you that theory is not only can help, but it's really essential in some cases. So most. Yeah, so.
What they do is theory, right?
All right, so I mean, like here, theory to improve efficiency. That's a specific question.
But it means like simple models, or what?
No, I mean state of the art model, like large language models.
No, but what is theory? Why whatever they do, you can say it is math just because it deals with matrices and things like that.
Yes, but that's not related to efficiency. Like if you do a forward prop, it's a matrix vector product, right? Some kind of math. But here the question is really about efficiency. Can we use some math to improve efficiency, in the sense, improve the way we train these models.
No, but I can have some idiotic trick, like take the top 5 eigenvectors of that matrix and remove the rest of them completely ad hoc, but it's still math, right? Just because it deals with
yeah, if you want to call
mathematical
it math.
objects.
Here, okay, so I'm gonna ask a more specific, like, can we prove theorems in the, like, to improve efficiency in some sense, right? Does that make sense?
Can theoretical insights be?
Yeah, that's another way to see it. Yeah, exactly. Yeah. Right. So most of these models are, built using like this deep learning paradigm, right? Which consists of, I like to think of it as like the interaction of 3 components. So the first one is a deep neural network, right? So parametric model, maybe billions of parameters, if not more. And then you have the data, right? Is the second component. Generally corresponds to something like, consists of like input target pairs. So in the case of large language models, the input would be like some sequence of tokens, and then target will be like the next token. But also you can think about images and labels and all kind of data. And then once you have these 2 components, basically the third component that connects the 2 is the training algorithm. So training algorithm will take the data and update the neural network using that knowledge from the data. It's usually done via this like a paradigm of empirical risk minimization, right? So you define some loss, and then you minimize basically this loss with respect to the parameters of the network. And the most famous way to do this is like stochastic gradient descent. You just take this gradient steps in the direction of the steepest descent, and using some hyperparameters like the learning rate, for example, or as people in optimization like to call it step size. They can also think about batch size. So this is like how many examples you use at each step. So all of these constants here, so the learning rate, the batch size, are called hyperparameters, right? So hyperparameters, and there are many of them. So you can think about the way we initialize the model. That's a hyperparameter. You can think about the learning rate. You can think about the batch size. You can think about the activation function. So a lot of hyperparameters in these models. And the way we select these hyperparameters is usually via hyperparameter tuning. So basically you set like a grid of values for these hyperparameters. You train the model with the different combinations of these hyperparameters, and then you pick the best one. So this is called like tuning hyperparameters, right? Now, when the model is small, this tuning hyperparameters is cheap, generally cheap, because you can train the model multiple times. You can afford to do that. But when the model is large, tuning this hyperparameters becomes very expensive, because you need to train the model multiple times, and it's just not cost efficient. And by large model here, I mean really I refer to 2 components. So the width and depth. You can think about the embedding dimension of the hidden layers. You can think also about the number of layers. So these are 2 ways we can increase the size of the model. Okay, so I'm going to call them width for the hidden dimension. I'm going to call depth for the number of layers in the neural network. And now, regarding the efficiency question I asked at the beginning, I'm going to ask a more specific question, which is, can we find a way to adjust these hyperparameters as we grow model scale? So the width and depth, right? Because as I mentioned, like it becomes more expensive to do that, to do the full tuning with scale. So can we find a way that tells us roughly where the hyperparameters should be? What's the range for the optimal hyperparameters? So more precisely, we're looking for something like this. So for example, if we're increasing the width, if we're scaling the width of the model, so increasing this embedding dimension of the model, we want some rule that tell us basically the learning rate, the optimal learning rate should scale roughly like this, should be in this range. So some constant times something that depends on depth. Because with this, the learning rate or the optimal learning rate becomes width dependent, and it gives you directly what's the range you should be looking for a good learning rate, right? Instead of doing like a full grid search with multiple orders of magnitude. Right. So to answer this question, I'm gonna try to convince you that we can study the limits where this width and depth go to infinity, to come up with such recipe or such scaling rules for the hyperparameters. Here's the learning rate. Okay, so I'm going to start with a simple example just to give you a flavor of what I'm trying to achieve here. I'm going to consider a simple neural network, two-layer neural network, linear, so there's no activation function here. So you have the input layer, which just projects the input from d dimensions to n dimensions, right? And then you have a second linear layer, w1 times y0, and then you have a projection layer, the last layer. Okay, I'm going to assume that the model or this weights w0, w1 in v are initialized using standard Gaussian distribution with some variances, sigma w L squared and sigma d squared. Okay. Now, for practitioners, you know, they want to scale the model, and when you scale the model, you pre-train from scratch. You need to reinitialize the model. Right, so you can think about what happens to one of these neurons. So let's select this one, for example, when the width is large. So as we increase the width of the model. So if we look at the expectation of the second moment of one of these neurons in this layer here, so this is the expectation with respect to the random initialization, right? And this is the expectation at initialization, so there is no training. So there are three scenarios generally as n grows. So either it will diverge, this expectation here will diverge as n grows, and this is, you don't want this scenario because this means numerical instability, so you don't want this. Or either it goes to zero. In this case, basically there is no learning because you can think of the asymptotic case where this is zero, all of this layer is zero, so there is no signal propagation during the forward and backward propagation, so there is no learning basically. So what you want actually is something like a stable limit, where as you increase model size, you want the neurons or these features here to remain stable. So nothing explodes, nothing goes to zero, nothing vanishes. Of course, this will depend on how you choose sigmas with respect, or how you parameterize the sigmas with respect to the width, right? How you adjust the sigmas with respect to the width. Okay. So let's do the simple calculations to derive such rules for initialization. So if you look at the input layer, this one here, if we do a simple calculations of, let's say, the expectation of the second moments of one of these neurons here, like simple calculations will show that this is equal to d, which is the dimension of the input, sigma w0 squared. This is the variance of the initialization that we used for w0, and we have the norm of x, the input squared. So you can see here that this formula here doesn't depend on the width n, on the dimension n. There is no dependence on it. So basically, as we scale the width, we don't have to worry about changing sigma w0 because this is theta 1 in n, theta 1 in width, no matter how, you know, that width is large, right? You don't have to adjust the way you initialize w0 in a sense, because and the reason is just because the input dimension here is fixed, so d is fixed. Okay. Now if we move to, so this is for the first layer, the input layer, right? If we move to this first layer, so this one here, and we do the same analysis, this time, if we do this calculation, we'll find that the expectation is equal to n times sigma w1 squared, so the variance we use to initialize w1, times this, basically the magnitude of the input feature, or the input layer features, this one. So if you want this to remain stable as you scale the network width, then you need to set sigma w1 squared to be something that scales as 1 over n, 1 over the embedded dimension. Okay. And by the way, this is not new. This was done in 1994 by Radford Neal, who is currently at Toronto. And he did this in his PhD thesis, where he studied like Bayesian learning for neural networks. And more recently, this kind of initialization is known as lacuna initialization or He initialization, but it's really similar in flavor too. And the idea is really to guarantee this stability as you scale the model. Okay. This gives you an idea about what I'm trying to achieve. So with this simple analysis, we can get a good idea of how to initialize the model as we scale the width or the embedded image. Okay. And by the way, this is the default initialization in practice. If you're using PyTorch or TensorFlow, any of these packages, this is the default initialization. It's called 1/fan-in initialization. Right. So I'm gonna give you like a timeline, a short timeline for infinite width neural networks. This is not a comprehensive lecture to review. It's just like the main, basically, research directions. So I think the first time the large width neural network, infinite width neural networks were studied in the literature were in the context of approximation theory in the 80s. Then the first time I think this infinite width neural networks were studied in the context of like methodology, was by Neil in 1994, and this is what I showed you in the previous slide. So he derived this 1/fan-in initialization. But then in the years like 2010s, I think you can find probably like hundreds, if not thousands, of papers on this like neural network Gaussian process and neural tangent kernel, mean field, the 9/15, which like Peter and Misha and many other researchers worked on. But yeah, there are hundreds at least, if not more. And more recently, I think this is a little bit like a different direction, which basically considers hyperparameter selection with scale. So how should we set the hyperparameters as we increase the model width or model depth, etc. So this is if you're familiar with like a edge of chaos initialization or maximal update parameterization, this is the kind of direction I am referring to here. And the work I'm going to talk about today is LoRa Plus, which is part of this direction, but more for fine tuning instead of pre-training. So this is a joint work with Nikki Ghosh and Ben Yu from Berkeley. And here we discussed or we proved that one of basically the most popular methods in fine tuning called LoRa, which I'll introduce in the next few slides, is suboptimal in the way it is used currently. And there is a simple hack to make it more efficient. So raise your hand if you ever, like, if you know what fine tuning means, just to know how much detail I should go. All right, so I think most people know it. So basically, yeah, fine tuning is really is a method to specialize pre-trained models in a way. So you can think of having some pre-trained pre-trained large language model, and then you have some task-specific data that you want the model to be basically improved on that data. Then you take that data, you take that model, you fine-tune the model on that new data to get a fine-tuned model. And the most natural way to do this is basically to just continue training the pre-trained model, but on the new data, right? You can just keep updating the weights of that model. Now, the issue with this method, which is called full fine-tuning, is that when the pre-trained model is large, so you think about like llama 70 billion or llama 400 billion, something like that, then this is very expensive. You cannot just take that large model and fine-tune it on like a consumer-grade GPU, right? So you need like a large server or large cluster of GPUs to do that. So to solve this problem, researchers introduced this like fine-tuning methods called resource-efficient fine-tuning methods, which basically the idea comes from the simple intuition that you have a pre-trained model, you don't need really to update the whole model to just make it better on a small task, right? So you can just update like small parts of that model and it will be better on that side. So this is called like resource efficient fine-tuning. One of the most successful methods is called low rank adaptation. But there are other ones like prompt tuning, etc. But in this talk, I'm gonna consider only the low rank adaptation method. So what is low rank adaptation? So you can think of the pre-trained model as some number of hidden layers, right? Each one of those layers has some weight matrices. So you can think of this W here as some weight matrix from the pre-trained model. And low rank adaptation basically considers this simple reparameterization of training or of fine-tuning. So instead of training this W, we'll fix the W and add a low rank matrix to that W and only updates the low rank matrix. So the low rank matrix is parameterized as B times A, where B and A has this have this shapes. So it's like a transposed shapes in a way. And the rank here is R, right? So the rank of B times A is R. And usually R is much smaller than the embedding dimension. So you can think of N as of order maybe 10,000 or more, and R is like 16 or 30, something like that. Right, so it's like the difference is really big. So the good thing from like by using this low rank adaptation, what we gain is in terms of parameter efficiency. So instead of doing the full fine tuning, which requires training this W, which is the pre-trained weights, it has n squared parameters. What we're gonna do is basically train only this lower part, right? It's low rank adaptation. It has only 2 by n by r parameters. So when r is smaller than n significantly, then the number of parameters here is much smaller than, so 2nr is much smaller than n squared. Right? And the way this is done in practice is basically using Adam to update A and B, right? The matrices A and B. No, Matches introduced Adam this morning, so I don't have to say much about it. But you can think of this as basically same as gradient or stochastic gradient descent, but G here is like a normalized gradient or some process gradient. You have like momentum plus normalization, you get something like this. Right. I'm going to show you that basically this training dynamics are suboptimal when the embedding dimension is much larger than significantly larger than the LoRa rank, which is a practical scenario. So to give you the intuition why this is the case, I'm gonna assume that we have like a simple linear model that's given by this. So like the output is Z out, and we have some input Z, and W is fixed, and we only train BA. We can minimize some square loss or something like that. So Z here is frozen in the sense like we don't change Z. It's an input. Okay. So when you do one Adam step, basically the new output that you get after taking that one Adam step, call it Z out dash. So this part here doesn't change, right? Because W is fixed. Now when you update B and A, so you get like B plus delta B. In A, you get A plus delta A. So if you expand, you get something like this, right? So if you look at the change in the features in the outputs, so Z out dash minus Z out, you get actually these three terms. So basically what I did is just expanded this 1 by Z, that's it. So you get these 3 terms. I'm gonna call these terms, this one here delta B, this one here delta A. And if you look closely at these terms, so one of them, this one here, it actually captures the contribution of updating B in the feature update, right? So here A is from like the previous step, we have delta B. And here we have B, we don't update B, and we have delta A from the previous from the Adam step, all right? So basically this term is responsible for basically represent a contribution, or let's say connected or linked to the contribution of B in the updates of these features. And this one is corresponding to the update of A in the feature change that we gave. So basically the way to think about this is just when you update A and you freeze B, this is what you get. When you update B and you freeze, when you update A and freeze B, you get something like this, and vice versa, right? Let's just forget about this third term for now. We don't have to worry about it. So now with this, we can ask the same question that we asked at talk about this initialization scheme. We can ask the question that what happens to this delta A and delta B as the width grows? So we fix the LoRa rank R, and we take the width to infinity, and just ask what happens to this feature updates here. delta A and delta B. Now, in a similar way to what we saw for initialization, you don't want this to explode, right? You don't want this to diverge as n grows. And you don't want it to vanish, because think about the case where, for example, delta A vanishes. It means that asymptotically, when the embedding dimension is large, this is negligible, which means that updating A doesn't affect the feature updates. So updating A doesn't contribute to fine-tuning the model asymptotically. So you don't want that. You don't want delta A to be small o of 1. You don't want it to go to 0. So actually similar to the same to what we've seen for initialization. You want something that's stable, that guarantees feature learning, right? So something like this, θ1, which means that when you update A, you get something significant, even for large width. It doesn't diverge. It doesn't go to 0, right? So you want something stable like that. Now, in this paper, we show that basically, if you use the same learning rates to update these matrices A and B with Adam, then it is impossible to have both delta A and delta B to be θ1 in that limit. So usually the scenarios you have are either like you have one of them is θ1 and the other is like go to 0, which means that it doesn't contribute to significant updates in the features. Or you get something like omega n, which basically something that diverges. So it is impossible to have both equal to θ1 with respect to width. And to solve this problem, we kind of reverse engineered this issue. It said, what would we want to force this? Basically, we want to have both θ1, right? So what should we do to achieve this? And by reverse engineering this problem, we found that actually what you need to do is decouple the learning rates for A and B. So you need to use different learning rates to update the matrices A and B. So for A, usually you need something that scales as 1 over n, and for B, you need something that doesn't change with them. And I think the intuition behind this is I can say it's simple once you see it. But basically, so B has this shape of n by r, right? So when you multiply B by any vector, there's also, when we do those calculations, it's always a sum of r terms, right? When you update B, you don't need to scale that learning rate to have stability, because it's just a sum of r terms, right? I can say more about this if you're
Isn't this the same as the famine, 1 over the famine?
So here you can think of it as finite, yeah, exactly.
Same as in the
For learn.
the earlier one, right?
So this is for the learning rate, not initialization. For initialization, 1 over n. Yeah, this is the learning rate. Yeah. Yeah. So in practice, what this means, because of this constants here in the theta's, what this means is basically when you want to update these two matrices, you need to set the learning rates for A and B such that the learning rate for B is much larger than the learning rate for A, because of this asymptotic behavior, right? So one of them goes to 0, the other remains constant. And just to give you an idea about the proof, so if we look at the expressions of this delta A and delta B, so this is again like the G are the Adam gradient, right? We can show that basically the GA times Z, so GA times the input, if you look at the components of this vector, asymptotically, they have this magnitude, like the scale of theta of width, right? And we can conclude from this that the optimal learning rate or the size of the learning rate that we need to have in order to have delta A equals θ1 is something like this. So θ1 over n, right? To kind of compensate for the magnitude of this term here. The same thing for B. So for B, we conclude that eta B should be theta of 1, right? And basically, just to conclude regarding this LoRa plus, the only difference between LoRa and LoRa plus, which is our method, is in the training dynamics. So we decouple the learning rates. And we set a lambda here in front of the learning rate for B. So you get the effective learning rate for A is eta, and the effective learning rate for B is lambda times eta, where lambda is much larger than 1. Okay. And just show you some empirical results. This is what you get with LoRa, so the orange curve, and this is what you get with LoRa plus. This is the results of fine-tuning a LLM called Roberta based on a language that's called MNLI. So you can see the effect of that small change, that small hack in the learning rate. If you want to use LoRa Plus, it's part of the Hugging Face PEFT package, which is like a package for parameter efficient fine-tuning. Just to conclude, to move to the second topic. So basically what we did is we found that different learning rates for A and B results in improved feature learning, summatorily. By feature learning here, I mean that delta A and delta B are both θ1, right? So they contribute significantly to the feature updates. We found something that's interesting in our empirical results. We found that LoRa Plus is most useful when the task is hard enough for the pre-trained model. So when let's say you take Llama 7B with MMLU, something like that. So you'll find that LoRa Plus is better than LoRa because actually when the task is hard enough for the pre-trained model, then you really need that efficient feature learning to efficiently update or train or fine-tune the model. Okay. One of the limitations of this analysis, because it's an asymptotic analysis, we have a lot of constants in those theta's, in those bounds. So the optimal ratio between the learning rates of A and B is not something that we get from the theory. We found that this optimal ratio, so by empirical evaluation, we found that this optimal ratio seems to depend on the model in the tasks. So the model here is the color, so GPT-2 and Roberta. Also, the x-axis is the task. You can see that the optimal ratio seems to be task and model dependent. But we found that a simple rule to select a good ratio between eta A and eta B is just to select lambda in this grid here. So 2 power 4. So from this grid on the first 100 to 1,000 iterations. So this is a very negligible cost. Actually. When you do fine tuning, like the first 100 steps or so of fine tuning is relatively cheap to do. So if you select this optimal lambda on the first 100 to 1,000 iterations, it will generally remain the optimal throughout the full. Yeah, sorry. Yeah.
Question for Soufiane. So
yeah,
it seems the theory suggests the best lambda should be like a n over r or something.
Yes.
So how does that number compare to n over r?
That's a good question. So the theory suggests that optimal lambda is theta of n over r. Right. So in theta there are a lot of constants. And those constants will depend on the model and depend on the data. That's the issue. We don't have like a closed form solution for this one.
I mean, if the features are normalized, then the constant follows by section.
Yeah, I mean, you can assume that you have some constant there, some concentration, but we don't have a closed form like solution for them, so we cannot estimate them in a way. The only way to estimate them is using some grid search or something like that.
But couldn't you just fix one of these and increase the width and then?
Sorry,
Couldn't you numerically estimate the constant? I mean, it's a relevant question. The question is whether this thing should be scaling with n or not. And
so okay, so that's a good question.
One of the
I think I should go to the theorem so I can. So basically, from this theorem here r is fixed and n goes to infinity, right? Here from this theorem, basically the optimal ratio scales of theta of n, right? So you can just take the ratio here. But the constants in this theta are implicit in a way.
Right. So yeah, I think we're all saying get rid of the constant by fixing our architecture and taking n to infinity and seeing if we're seeing the growth of n in that log ratio plot.
So you mean numerically, right? So you see it numerically. Yeah, that's exactly. So this is what we suggested actually.
Repeat the experiment for 3 different values of n, plot in log-log scale, and see whether the power law that you predict is correct.
I'm not sure that's an interesting. Okay, so because that will depend on the constant there will depend on the data and the task. It will depend on the model. So if you fix both, then yeah, probably we haven't thought about that. But there is a limitation to that actually.
Just trying to translate what.
That's a great question. But now that I understand your question, the main limitation there is you don't control the pre-trained model. A pre-trained model is there. You cannot scale it.
But you fix it.
Yeah, you fix it, but you cannot increase n, right?
But you increase, okay.
That's the issue, right? The pre-trained model is there. If you want to do that experiment, you have to pre-train that model multiple times with different embedded emissions. Yeah.
But the ratio should look like n over r, and you can.
Yeah,
vary
exactly.
r.
Yeah.
You could do the experiment by varying r.
So basically, all right. So that's a good question. So I have that experiment somewhere when I vary r, but it's not nice to see. Like it's unstable.
Interesting. So you've done that one, and
Yeah,
it's
yeah.
not.
I have it with r. Yeah, when we
And it
vary r.
doesn't grow as 1
No.
over r.
No. Because theta is like it's like a range, right? It's not a, yeah, that's the issue.
So this was all for Adam, right?
Yes.
So
Adam-like algorithms.
yeah. So what about gradient descent?
No. So you need that normalization. You need the normalization in the gradients. Otherwise, it doesn't work.
Okay. So there just exists no way to do it with gradient descent.
You mean the theory or?
Yeah.
I haven't. So we have some theory with stochastic gradient descent, but from the beginning we considered Adam-like algorithms like sine HGD or Adam.
Yeah.
So that normalization is key assumption. Is a key assumption. Yeah.
How many iterations is the overall when you run the thing?
So for fine tuning.
Yeah, for fine tuning.
Yeah, I mean it depends on the task, but usually it's like 10 epochs. So that would be like order of 30,000 iterations. Yeah. It depends on the task. Like when the task is hard, you probably need more, and when the model is large as well.
You had a plot where you said that you had like a 2x speed up. Could you explain that a little bit? I didn't
Oh, yeah,
quite understand the
yeah.
2x speed up.
Yeah, so basically here what we mean by speed is just like what's the number of steps you need to reach like the same accuracy that you reach, the best accuracy that you reach with LoRa when you use LoRa plus. So you need half the steps to reach like the same accuracy.
I see.
Yeah. So yeah, so basically LoRa plus you can think about it as like either you fix the number of steps, you improve accuracy, or you basically reach the same accuracy with fewer number of steps or something.
Very cool.
Yeah. Yeah, so just to conclude with this, basically, we found that the best way to select lambda, or the cheapest way to select lambda, this optimal ratio, is just by doing like a grid search. And that's the best way to do it in practice.
Yeah. So do you really need to try all 4 of them?
Or is there one that always works?
So we found that this grid should be sufficient for most of the practical cases, but yeah, I mean, this is not like a solution for everything. Like
I just mean because doing a grid search in practice is just not really an option. So
why isn't it? No.
It's like $100 million. So
no, but this is a grid search on the first 100 to 1,000 iterations.
But still, it's
no, this is negligible cost in practice for fine tuning.
Also a grid of size 4, right?
Yeah.
It's not.
No, I mean, I know what you mean, but what you're referring to is like training the full model from scratch. That would be like hundreds of millions of dollars, something. But this is fine tuning. The task is small, generally, and you only do this for the first 100 to 1,000 years. So you don't need to run the full fine tuning.
well, but you were also saying it's a 2 times speed up, but you're paying 4 times, so it's double.
No, okay, so I think the confusion is here. So this is 35,000 steps, right?
Yes.
What I'm suggesting is to select that lambda, the optimal lambda, on the first 100 to 1,000 iterations. So something like you only run like this, here somewhere. Does that make sense?
Kind of. I just feel like if there was a way to get a 2 times speed up in practice, people would be doing it. So
I'm not sure I understand your question. Can you repeat it like more?
no, I just mean that for any one of these like simple things,
Yes.
practice always finds them. They're very good at finding them.
Yeah.
So
That's a theorem.
Yeah. So I think like if you of course like if you find a cheaper way to do that, then that's always better, right? What we're suggesting here is that basically the gain from using LoRa plus in selecting this lambda here is bigger than just using LoRa without doing this. Because this is a negligible cost. Right. So, okay. So there are no other questions. I can move to the second question, or the second example in this talk. And here I'm going to talk about depth scaling. It is more for pre-training, not fine-tuning. It is the result of like collaborations with amazing researchers from all around the world. So just again to give you like a timeline for depth scaling. This is not a comprehensive literature review, of course. So I think the first attempts to scale depth, so increase the number of layers in a deep neural network, like really with significantly large neural networks. So it was in the case of like was with MLPs in the convolution neural networks, which mostly failed. And the reason behind this was that as you increase the depth of these models, you have this problems of gradient exploding as you do the backpropagation, gradient vanishing, or you get like this signal issue with signal propagation. So as you increase the depth, the information seems to be like to fade away in a way, to be lost as it propagates through the network. I think a significant contribution in the field was with the introduction of ResNets, or residual neural networks, in 2015, which basically, so again, this is empirical work, right? None of this is really like a theoretical analysis. So the introduction of ResNet, we could scale this neural networks up to a reasonable depth, so something like 30 layers, 40 layers, something like that. But then, oh, sorry. Yeah, something like that. So AlexNet was like stuck at 10 or something like that, and or maybe 15 something. So with ResNet, you can train like 30, 40 layers. That was the, and the reason behind ResNet, like the intuition, although there is no theory, the intuition is to guarantee this like signal propagation because of that residual connection, and also to prevent the gradient vanishing as it backpropagates. Okay, but then quickly after that, between 2015 2018, I think people started to notice the stability issues in ResNets, also transformers. And here in this period, you can see like a lot of papers on normalizations, you see batch norm, layer norm, all the kind of stuff. And the reason was really the motivation was really to fix the stability issues as you increase the number of layers. And more recently, like people started to also ask the same questions that we've seen for the width. Now, how to select the hyperparameters with depth as you increase the number of layers. You can, in this case, I'm going to talk about stable ResNet and depth myopy. But just know that there are other theoretical works that consider the different aspects of scaling depth or increasing the number of layers. So there is one from 2014 on expressivity. Look at how expressive is the network as you increase the number of layers. There are also like some papers that study the gradient descent for large depths. I think Peter and Pierre worked on this. Yeah, so here I'm really referring to hyperparameter selection as you increase depth. So that's a different problem. So I'm going to consider a simple residual neural network. So it looks like this. Basically, you have some input layer, then you have some hidden layers. This is called the residual neural network because it has this term YL-1. This is the reason, like basically the idea or the intuition is that instead of writing YL as a function of YL-1, like directly like this, like the MLP layer, you write the difference between YL and YL-1 as a function of the previous layer. So you're kind of learning the residual in a way instead of YL directly. Okay. So I'm gonna call again like the number of hidden layers, the depth, the width is the embedding dimension, and the phi here, this is a nonlinearity called activation. So one of them is ReLU, which phi the linear unit. It's going to take just the maximum between z and 0. So if you know transformers, Oh, sorry, this are constants. Forgot to mention this. The lambdas here are constants. In practice, they're usually equal to 1. So they're fixed to 1. Okay. So transformers are the neural networks behind large language models are also residual networks, right? So they have this structure, YL equals YM minus 1. The difference is in this block, so it's more complex. So it has this self-attention mechanism plus MLP. But essentially, they have the same structure. So I'm going to ask the same question now with respect to depth. How can we select the hyperparameters as depth grows? And here by hyperparameters, I mean the lambda here, this constants in front of the block, and the learning rate eta as the depth L grows, so the number of layers, right? We're going to show you like a simple simulation where here I show the last layer. So these are the neurons in the last layer. The embedding dimension here is 8. We have 8 neurons here. And the y-axis is the values of these neurons. So here I just ordered them by value, basically. Right. And I'm going to show you what happens to these neurons in the last layer as we increase that with this architecture here. And this is at initialization, so I didn't train anything. So if you look at the y-axis, you see something interesting, which is that as depth grows, those values on the y-axis actually grow exponentially with depth. Right. So this is what practitioners refer to as like exploding features or exploding pre-activations, and also you can see a similar behavior for gradients. And this is why this is like the main motivation behind this normalization solution, like batch norm, layer norm, all that kind of stuff. So now if I do like a simple modification to the network and I introduce 1/square root of depth here, a very simple modification, you can see now that the behavior of these neurons completely changed as you increase the depth. So the y-axis, you see the values there are like very stable, so nothing grows with depth. So you get like stable features, ingredients, and when you do this, at least at initialization. So this is a very simple mathematical result. Basically, if you put the lambdas here on the this constant, and you initialize the weights with the 1/fan n, this is the width, so n is the width. You show that basically the expected value of any neuron inside the network scales asymptotically in depth like this. So it's like theta of exponential of 1/2 sum of this lambda squared here. Right? And from a practical perspective, what this means is basically if you want these neurons to be stable as you increase the depth of the network, you just need to make sure that this thing here is stable, right, with depth. So basically, depth stability is equivalent to just having the sum of lambda squared being bounded as you increase depth. And so one of the simplest choices for the lambda is 1/square root of depth. So the sum of the lambda squared in this case is equal to 1. So that's always bounded. So it doesn't change as you increase the depth L. And by the way, when I read the GPT-2 paper, I found that they used something similar to this, but the difference is that they kind of merged this lambda in W. So instead of putting the lambda explicitly here, they actually initialize the W with something that scales also with depth. So it's like a hacky way to do that, basically. Instead of putting a lambda here, just put it in the weights directly. This is what we call stable ResNet. Any ResNet that any residual architecture that satisfies this condition. I think the easiest one is like 1/square root of depth. So you put it there, and this is what I showed you in that simulation. So you put 1/square root of depth. Yeah.
Question: why do we care about this notion of stability? Like, for example, I think we should care more about the trainability of like standard algorithm, right? Like having exploding activation value doesn't necessarily mean it's not trainable.
That's a good question. So basically, stability, you want stability because of numerical, you want numerical stability in the code, right? When you train this neural networks, you are like computing the forward prop and the backward prop, and each one of them is like, you know, some value. So basically, if you, I'll show you like in the experiments that if you don't care about that stability, at some point training fails completely.
I mean, like when you're using like a low precision format like BF16, things goes wrong. But if you use higher precision,
so the precision is always bounded, right? We don't have infinite precision. Like the best you can do is like 32, 64, something
64,
like
yeah.
Yeah, and you don't want with any precision, you don't want that numerical instability. It just, you know, it makes sense from like a practical perspective. But I think from a mathematical perspective, you can say, why not just like keep things like exploding and just compensate in the last layer, something like that.
Right.
But so that makes sense from a mathematical perspective. But when you do the calculation, like the numerical calculations, you want everything to be stable. That's just more efficient and more.
Okay, so the answer is the main reason here is for numerical stability.
Sorry, say it again.
So the conclusion here is the stability notion started here is mainly for numerical stability.
Yes.
Okay.
Yeah, exactly.
Thank you.
Yeah. All right. So, yeah. So actually, we can, if we put the 1 over square roots of depth here in front of this block, we can actually show something more theoretically something more interesting. If we initialize the weights with the 1 over fan n, then in the limit, when we take the depth to infinity, we can show that the layers of this neural network actually converge to something like a stochastic differential equation. There's a concurrent work by another author, well, other authors who showed like something similar, but with more general settings, so more general activation functions, etc. But this really gives a nice idea about like the behavior of this network at initialization, of course, when you take the depth to infinity. So the way to think about this is basically you can look at this neural network here, these hidden layers, and think about them as having like some discretization of an infinite depth neural network or something like that. So just to show you some empirical, yeah, sure.
Paper also, I'm just looking at it by Li and Nguyen, 2019. They do some infinite width, you know, this Gaussian evolution at initialization.
Yeah, I mean, there are many of them, yeah.
ICL.
Which one are you?
Li and Nguyen, I'm just looking.
Can you tell me like the title?
Oh, yeah. On random deep-weighted tied autoencoders, exact asymptotic analysis, phase transitions, and implications.
I think I know what you're talking about, yeah. But that's for the weight, right?
No, it's, I mean, okay, I'm just browsing through it. It talks about infinite depth, but okay, I mean,
okay, so there are like a lot of papers that consider like infinite width and then try to look at the signal propagation with depth. So one of them is like edge of chaos. I think you're referring to one of them, but there's like a whole directional signal propagation, probably one of them, yeah. But so here, like it's very specific to this residual neural network. I think you're referring to MLPs. Yeah. Okay. Yeah, I think I know what you're talking about. Yes. Yeah. So with this residual connection, connection here, like the YL-1, you get this limiting behavior, which is an SDE basically. I think probably I should. Okay, but just to show you some empirical results. So here, these are the numerical results with when we train a neural network with on CFR10 with Adam, learning rate eta. So the x-axis is the learning rate. So eta, you see like a grid, basically. It's like a grid search. And the y-axis is the loss. So the smaller, the better. So the left figure here is with lambda equals to 1, which is basically we don't scale the block. And the right, the figure on the right is with lambda equals 1 over square root of depth, which is which we call like stable resonate. And the color code is how deep is the neural network. So the darker, the deeper. So you can see here that with the standard setup, and unfortunately, if you use PyTorch, this is you are in this setup here. So if you increase depth, you should be aware of this issues, right? As you increase depth, at some point the training completely fails, and that's really because of the numerical instability that comes with depth. Now, if you just add that 1 over square root of depth, you see that it becomes much more stable. In the training loss actually improves with depth consistently. Right. And there is one issue here that I want to mention is that although with this normalization or with this scaling in front of the residual block, we improve the loss, right? So you can see that it consistently improves. The optimal learning rate, so the x-axis, you see that it it shifts towards the left. So there is a significant shift of the optimal learning rate with depth, right? So what's the learning rate? What's the optimal learning rate that we should use to train a depth L model? So the optimal one for this depth here is this one, but the optimal one for the deepest model is this one. So there is a significant shift, like 4 orders of magnitude, something like that. Okay. So to study this, we did the we assume here that we put 1 over square root of depth in front of this residual architecture, and now we parameterize Adam learning rate with depth as well. So we put like eta times depth to the power minus gamma, something like that. Gamma is some constant. So we found that we put this in this is what we call depth mu p. I'm going to explain what that name means. So we proved that actually when you take one Adam step, the change in the features between step t and step t minus 1, right, for some hidden layer, right? Actually, that change is on average theta 1 in depth, if and only if this gamma here is equal to 1 over 2. Right. So again, this theta here, this theta 1 is coming from that intuition of stability. So you don't want things to go to 0, you don't want them to fall, you want them to be stable. And to have this stability with Adam, stability in feature learning, right? Because if this is like small o of 1, that's still stable. That is stable, but you don't have any learning in the limit. So you want theta 1 because that guarantees some significant learning in that limit, and also guarantees that nothing explodes. So to have that condition, we need the gamma here in the learning rate to be 1 over 2, which means that the optimal learning rate should also scale as 1 over square root of depth. So this is like the depth equivalent of mu p. So if you're familiar with the maximal update parameterization, this is the depth equivalent of it. Okay. We can actually, I think I'll just skip this. Maybe someone asks me about this. Just to show you some empirical results. This is what I showed you before with the stable ResNet, where we didn't scale the learning rate with depth. But here, when we add this condition or this result from the previous theorem that tells us how the learning rate should scale, then you see that the optimal learning rate seems to become stable as you increase depth. So for example, the optimal learning rate for 2 to the power 10, like a 1,000 layers network, is approximately the same as the optimal learning rate for this network, which is like 2 to the power 6 layers, something like that. And this is what we call hyperparameter transfer across depth. It's good because basically instead of tuning that eta for this 1,000 layers neural network, you can actually tune it just for this neural network here with maybe 100 layers or even less, and use the same eta for the 1,000 layer neural network. So the optimal hyperparameter transfers across depth. Okay. Just show you some results on transformers. So this is like a transformer network called Megatron, trained on a data set called Common Crawl with Adam. And here what I show you here is like the optimal learning rate, the learning rate eta times square root of L. What I want to show you is that the optimal learning rate times square root of depth seems to be stable as you increase the depth, right? This kind of confirms the theory, but for more advanced models, transformers. Okay. So just to summarize the two examples, so basically with the infinite width and infinite depth analysis, we kind of using this simple analysis, we get some idea about how to parameterize different learning rates as you increase one of these dimensions, right? So one of the scalable dimensions, either the width or the depth. And if we look at how these models are pre-trained or fine-tuned in practice, there are many inefficiencies in how this is done. And I think in a lot of them, it is almost impossible to identify those inefficiencies just empirically by just like running multiple experiments and try to find where is that inefficiency. And so you think about like LoRa Plus, for example, it's really hard to get that intuition to decouple the learning rate without doing like an analysis to see where that feature learning breaks. So I think a theory of scaling is really important to identify these inefficiencies. Although in some cases it might be like a physics level of rigor if you cannot do it on like the neural network itself, or maybe you consider like a simple model to do rigorous theory. But I think in just by considering the scaling limits, you can identify a lot of inefficiencies in how to set the learning rate, how to set the hyperparameters as you scale the model. Okay, I think I'm just gonna finish with some open questions. Yeah, so there are like many scalable dimensions that I didn't talk about in this talk. I talked about the width in depth, but you can also think about the data limit. We take the data to infinity. This is more like a traditional statistical setting where you consider data going to infinity. You can think also about test time scaling right now. That it's like in this context of reasoning models, what's the best way to scale test time? And also think about other hyperparameters. So I know that Jianfeng worked on some behavior, like considering how the optimal batch size should scale with width. We did also some work on the how to adjust the activation function as you scale the depth of the neural network. There are also like can even generalize this to other limiting properties of the model. So instead of just wanting that stability in the limit, you can ask like, we want something more than that. Maybe we want even the model to be aligned, to remain aligned as we scale or something like that. That's a more complicated property, but we can think about this kind of questions. Also, something I didn't mention is the commutative limits, or okay, more precisely, like I considered the infinite width limit and then consider the infinite depth limit. But what happens if you take both to infinity at the same time, or at some fixed ratio, something like that? So we have two papers on this kind of these questions where we show that with the residual architecture, the width and depth limits commute actually. So no matter how you take those limits, you get the same limit, the same limiting behavior. Of course, one limitation of this is that the results are only valid at initialization, but my conjecture is that it's also true for like during training, take a fixed number of steps. Yeah, so forget about self here. It was something that I introduced in the previous slide. But basically, another open question right now is like scaling laws. So the scaling laws are basically like the data and parameters limit, right? And when you take them to infinity. Currently, there is very little theory on this, mostly from like a linear regression perspective. But there is almost like no theory on this that gives us this kind of results. I think that it would be very interesting to study this kind of limits as well. I'm gonna conclude with this figure. I like to always show this figure. So what we saw in this talk is basically two components of deep learning, so neural networking training algorithm. I didn't discuss data, but actually there's a whole other like components of efficiency, which is the hardware part, and that's the GPUs, the storage, how these chips are connected, etc. And there are a lot of works on that side of efficiency. So for hardware, like flash attention, KV cache. So the latest work on that shows like really the importance of efficiency from a hardware perspective is the DeepSeek, right? To use this, they really did like a great job in, making the hardware more efficient. And just to conclude, I think the future of studying efficiency at scale is really like an intersection of theory, some theoretical analysis, but also an engineering to take the hardware part into account. But that's it for me. Thank you.
Any quick questions? No, let's thank speaker again. And we will have a 30-minute break.
Yeah.